everyone. Today I'll be talking about the low frequency analysis roadmap. So in the low frequency region of the single stage VGD or FET amplifier, it is the resistive and capacitive combination, the resistor and capacitor, formed by these network capacitors, collector, the emitter of the source, and their resistive elements determine the cutoff frequency. So in fact, in RC network, similar can be established for each capacitive element and the frequency of which the output um, drops to 0.707 of its maximum value can be determined. So kung asa to nag 0.707 ang output voltage with respect sa input, mao na siya ang ginatawag na cutoff frequency. So once the cutoff frequency due to each of these capacitors are determined, now they can be compared to establish kung unsa nga mga resistive element and capacitive elements that will determine the cutoff frequency. So mo na tong goal. So pangitaon nato ang value sa resistor, capacitor, ang frequency nga resistor, capacitor, cutoff frequency. We will examine this circuit here, the generic RC combination. There is a figure 9.14. So once the result obtained, kung mainumduman nato ang reactive component for this RC circuit here, ma-determine nato unsa ang effect niya sa element or sa reactive reactants. So for the this circuit, if i-consider nato nga na siya sa high frequency, this one na siya sa high frequency. So 1 over 2 pi, let's say 1 times 10 to the power of gigahertz. Let's say 1 times 10 to the power of 9 times capacitor, any element. That would be infinity here. So 1 over infinity is approximately 0. So previously in our discussion, it was been mentioned that once we have this frequency at high frequency, ang iyang effect, mahimo siyang short circuit ang capacitor. On the other hand, if this circuit here, we apply a frequency approximately 0, then the capacitive element or the reactance would be, okay, just substitute, plainly substitute 1 over 2 pi times 0 would be an infinity. So 1 or anything under the zero, having a denominator of 0 equal to infinity. So mahimo siya, muak siya as an open circuit. So now we'll see on this diagram. So we have this low frequency response for an RC circuit previously shown sa katong figure 9.14. Okay, so we have here a circuit nga katong capacitor, then resistor here, then V out, then V in. So as we increase the frequency applied to the system, then the V out would approximately or approaches to the V in. So this would act as a short circuit. Then as you can see, magkataas ang atong frequency, ang atong voltage gain, magnitude gain is would approximate to equal to 1. So kataas atong frequency, magka closer to 1 ang iyahang voltage gain. And for next slide would just be, let's say this is XC, then V out is just equal to the V in times the resistor over the resistor plus the XC here. So that is the both ways here is considered for the apil na ang polar. So the magnitude could be determined by the root mean squared na lang. So we have RVI, or R times the input voltage, over the squared of the resistor plus the square of the capacitive element. So for a special case, whenever the capacitive element is equal to R, and then substituting the Xe into R, so we have 2R squared na. So the value of the output voltage is just equal to the 1 over square root of 2 times input voltage. So that would be the relation of V out over V in whenever the capacitive element is just equal to R. So when we have the value, or the ratio of the V out over V in, the magnitude gain of these elements, so 1 over square root of 2. So we have V out, let's transfer the V in, so we have V out over V in is just equal to 1 over square root of 2, or 0.707. So that is the case if ever Xe is equal to R. So that scenario is the case na ang Xe is equal to R is the value for 0.707, or the cutoff frequency, as discussed previously in our discussion. Whenever the value of the parameter is equal to 0.707 of that input parameter, mana siya ang ginaingon nga cutoff, the corner. So na-determine na to. Mo-occur na siya at Xe is equal to R. So given by that, we could determine the cutoff frequency na mo-occur lang siya at Xe is equal to R. So we have Xe is equal, the formula for the reactive element, or the reactive capacitance, so we have 1 over 2 pi f Lc. So since the case na Xe is equal to R, so we can just put R in the denominator. So we could have the frequency equal to 1 over 2 pi Rc. So we already have the formula to determine the cutoff frequency whenever we have the value of the R. So in a moment, with this, we will find the RC network. We'll determine the low frequency cutoff for a BJT transistor, and F will be determined by this equation. So we have the gain equal to V out over V in equal to R over R minus JXC. And we have, to simplifying this, we have to divide this both numerator and denominator by R. So we'll have to divide this both numerator and denominator. So simplifying that, so we have 1 over 1 minus jxc over R. And xc here is just equivalent to 1 over 1 minus j omega c. Times R na, kaya na-apil naman siya diri as R. And then, this omega here is just equivalent to 2 pi f. So we have 1 over 1 minus j 1 2 pi f CR. And this one, we know that earlier in our discussion, the FL is just equal to 1 over 2 pi RC. So this one here, not including the F, is just equal to FL. So substituting that, we can obtain the gain equal to 1 over 1 minus JFL over F. And this one is just the polar value, and to determine the value of the gain, and to get the polar value, the magnitude and phase, so we have 1 over square root of 1 plus square root of 1 plus square root of FL over R. And then the phase could be determined by the tangent inverse of FL over F. So this phase here determined by which the Vout leads the input voltage. So for the magnitude, when the frequency is equal to the cutoff frequency, we know that the voltage gain is equal to 1 over square root of 2, or equal to 0.707. So when we use the logarithm, the formula for determining the dB of the gain, so we have 20 log of 0.707, we have negative 3 dB. So 20 log of 0.0707 is just equal to negative 3. So that would be the value whenever the frequency equivalent to the low cutoff frequency or the corner frequency. So in the logarithmic form, we have 20 log base 10 times 1 over square root of 1 plus square root of FL over F. So simplifying this one, we have to simplify that one, raise this square root here into 1/2. So we have 20 negative, since this is from the denominator, so we have the negative here. So we have negative 20 log times 1 plus FL over F squared to the power of 1/2. And this, by the law of logarithm, we can put these exponents here into outside the logarithm. So we have negative 1/2 times 20 log 10 times this value. Then simplifying again, negative 1/2 times 20, so we have negative 10 log of this one. So whenever the frequency is very much lesser than FL, or the FL over F is F squared is much greater than 1, this equation here could be simplified kung dako kayo ni siya compared to 1. So this would cancel out. So the value of the gain would approximately equal to negative 10 log times FL over F to the power of squared. So this square here again, by law of logarithm, can be put here in near the constant. So we have 2 times negative 10, so we have negative 20 log FL over F. Whenever the frequency is very much less than the FL, or the FL over F squared is very much greater than 1. So a change in frequency by a factor of 2 is equivalent to 1 octave. This one. Let's say the FL over F, for example, let's say we have FL over F is equal to 1. So negative 20 log of 1 is equal to 0 dB. So whenever the frequency is 1/2 of that value of the low cutoff frequency, or double the frequency is the value of the low cutoff frequency, or the FL over F is equal to 2, or just double, then the value of the gain in dB is negative 6 dB. So this factor na ginatawag is equivalent to, is called a 1 octave. So isa na ni ka octave from FL to this one. Isa na siya ka octave. And this one also is 1 octave na, 1 octave. So the difference of dB in 1 octave is equivalent to negative 6 dB. Whenever also kanang i-change na to by a factor of 10, the difference, or in 1 decade, for example, change in frequency to 1 decade, the change of the gain in dB would be equal to negative 20. So kung i-change na to ang low cutoff frequency to 1/10 or the frequency equivalent to 1 decade, then the value of the gain difference would be a negative 20 dB change. So let's have an example here. We have this resistor and capacitive element. So our goal here is to determine the break frequency or the corner frequency or the cutoff frequency. So we already derived the equation for determining the value of the break frequency or the cutoff frequency using the resistor and capacitive element. So we'll just substitute that. And next one is to sketch the asymptotes and locate the negative 3 dB. So asymptotes meaning katong linya nga moduol approaches to a 0 dB. Next is sketch the frequency curve. So in order to get the approximate real value of the frequency curve, kinahanglan nato makuha pod ang asa tong negative 3 dB niya or the low cutoff frequency. And also we'll find the gate at or the frequency, the gate at the gain is equal to negative 6 dB. So the solution here, so first we already know the value or the formula for determining the cutoff frequency, so just substitute the value of R and C. So the low cutoff frequency is equal to 1/2 pi RC. So 2 pi is just equivalent to 6.28. Then the resistor is equal to 5 times 10 to the power of 3. Then the capacitor is 0.1 times 10 to the power of negative 6 farad. So substituting that value, we could determine that the low cutoff frequency would just be equivalent to 318.5 Hertz. And to sketch the asymptotes from negative 3 dB point, so we'll just use the values that we already get from our previous calculation. So from whenever the frequency is equivalent to the 1/2 of the FL, then we have negative 6 dB. So from here sa FL over 2, from here, ang drop niya is negative 6 dB. And for FL over 4, let's say this is FL over 4, naa siya dapat sa negative 12 dB. So from this, and FL over 10, katong 1 decade niya, the value approximately is equal to negative 20. So joining those points, we could form the asymptotes of the frequency curve. So kana siya na natay point dire, natay point dire, ug ang point dire, then sumpay lang nanto na tanan dira, then we can form the asymptotes. And for the frequency curve, the real frequency curve, makuha nato na, diba nakuha na nato ang cutoff frequency. So kung asa tong cutoff frequency niya, dito ang negative 3 dB. From that, then we can have the curve of the element, the circuit. So now, ang iyahan na pong gipangita is, so to find the voltage gain, not gate, rather this is gain. So find the gain at dB is equal to negative 6 dB. So the gain is equal to V out over V in, and we know by a formula that gain is equal to 20 log of V out over V in, ngayon siya negative 6 dB, right? So by using the anti-logarithm. So so we have negative 6 over 20. So anti-log lang. So when we say anti-logarithm, so we'll just raise this value by a factor of 10. So 10 raised to negative 6 over 20 is, or negative zero point 0.3 is 0.501. So the value of the output voltage is just approximately equal to the 50% of the input voltage. So by a value of 50% of the input voltage, we could get the gain approximately to negative 60. And for the correction here, this is gain again. So the assignment would be just same circuit, just replace the value of the resistor into 10 kilo ohm. So I think that's it for the low frequency both plot for a BJT amplifier. Next, we'll try to discuss the low frequency response of a FET amplifier. So thank you for listening.